This is the first in my series of videos on conduction, convection and radiation, so thermal energy transfers. This video will focus on conduction. So what I hope to do is give you an overview of what conduction is and explain some real life scenarios and then look at how it comes up in examined questions. So to understand conduction, you really need to have in your mind the properties of solids, liquids and gases. So hopefully you remember that solids have got touching particles in a regular arrangement. The particles vibrate in fixed positions and have strong intermolecular bonds. Liquids have got touching but irregular particles that can slide past each other, so they're not in fixed positions with weak intermolecular bonds. And gases are spaced out, or the particles are spaced out. They move quickly in random directions and they have no intermolecular bonds. You can change a temperature from one state into another by altering the temperature, and that is because temperature is a measure of average kinetic energy. The reason I've underlined average is because if you get asked that in an exam, that is worth a whole mark. So if you just said kinetic energy, it's worth 1 mark, but if you say average kinetic energy, it is worth 2. Because it's linked to average kinetic energy and kinetic energy is movement energy, this also means that it's linked to particle speed. So as you go from vibrating to sliding past each other to moving quickly, the particle speed is increasing. So what is conduction then? So this is a small animation that shows what conduction is. So we're going to start to heat the particles on the very left hand side here, and you can see that as the particles get heated, they start to vibrate more rapidly, and what's actually happening is they will collide with their neighbour, and because of the strong intermolecular bonds, when they collide in with their neighbour, they will cause the neighbouring particles to move, and that will carry on going through the substance. So let's try to write down a definition of conduction. So conduction starts off with particles close to the heat source start to vibrate more rapidly. Now it's really important that you don't just say start to vibrate, that you say vibrate more rapidly, so you show that it's the same but more than it was doing before, because all particles vibrating a little bit unless they're at absolute zero. So the next thing that happens is this causes those particles to collide, another key word, with neighbouring particles, causing them to vibrate more rapidly too, and in that way the thermal energy passes through the substance, or gets carried through the substance. So the next question we have to ask is, well, what type of substances, based on what we know about the particle models for each, make good conductors? And the first thing to do is to think about which state of matter would make a good conductor. Well, in gases, the particles are not touching and they're far apart and there's no bonds between them. So if this particle starts vibrating a lot, it would have no impact on the ones next to it. So gases are terrible conductors. With liquids, if this particle starts to vibrate, it's only weakly connected with the neighbouring particles. So again, conduction does not work very well in liquids. So conduction works best in solids because the particles are touching, and really importantly, they've got strong intermolecular bonds. So if we just take solids then as a state of matter, there's lots of different solids, and the ones that make the best conductors are metals. that is because metals have got delocalized free electrons, so if this particle starts to vibrate, it can actually kind of ping the particle quite far into the solid, and that would have, it basically just increases the impact of one strongly vibrating or rapidly vibrating particle on the others. You don't need to really be able to explain beyond the fact that metals have got free electrons, but that's just an indication of what's going on there. So how do we investigate this? Well, this is a kind of a classic investigation. What's going on here is that there is a drawing pin on the end of each of these pieces of metal. These pieces of metal have all got the same surface area and cross section, and they are just stuck to the end of the piece of metal with a little bit of wax. I've put it this way up in the picture so that you can actually see what's happening, but in reality we turn it over so the drawing pins are hanging downwards to do the experiment. So the thing that we are changing there in the four arms is the substance, so that would be our independent variable. The dependent variable is the time taken for the pin to drop, and the things we would have to control is the distance to the pin. We would need to control the amount of wax that we use to stick it on, the amount of wax, and the other thing is they are all over the same heat source, so they're heated to the same temperature. So how would we know which was the best conductor? Well, the best conductor is going to be the one that lets the heat through the quickest, so it's the one where the pin drops first. So there's similar experiments that work in exactly the same way. This one, you've just got a water bath here which would be filled with warm water, and you can see all of the rods are the same length and the same cross-sectional area with the wax at the end and the pins there ready to drop. This one works slightly differently, but you put all of the metals in the same depth of water, and this is actually a thermometer on the front, so you can gauge which is the best conductor by which gets the highest temperature rise. So this is also a kind of a classic experiment to get asked about exams, is if you take a baton that's half wood and half metal, wrap it in a sheet of paper and heat it over the Bunsen burner, with the Bunsen burner over the join between the two substances. So the question is, what happens next? Well, this is what happens. This is quite a confusing picture, but this side is the wood and this side is the metal, and above you can see a photo. And what ends up happening is, over the metal you can't see any charring of the paper, but over the wood you can do. So here is an exam question that is asking you exactly what's going on in that scenario. You can take a read of it for yourself and then give yourself 2 minutes to answer it, then play the video again and you can see the answer. Okay, so the first mark here is for saying the paper on the brass does not get as hot. The paper on the brass over the metal does not get as hot, and the reason for that is because the brass tube will conduct the thermal energy away from the heat more rapidly. Okay, so whereas with the wood this will stay hot, with the metal the heat is conducted away. So that's it for conduction. I've explained what it is, and I've explained a few different ways to investigate it practically, and I have also shown you how it typically comes up in exams.